So yes, there's office hours today at 3 o'clock. We'll switcheroo. Typically I'll be available on Mondays, but we're switching this week. All right, very good. So, last time we were reviewing some more fundamentals and introduced to some of you, or reviewing for others, this very, very critical idea of the density operator. So if we think about a quantum state as a vector in Hilbert space, when we express it as a superposition of some basis states, and then we would typically write the state this way. We can write it, if we want, as a column vector, if we have a d-dimensional system. And this is my notation here, a little dot here saying with respect to some basis. Okay, that's what I mean by that. And as we motivated last time, it's very, very useful and essential, as we will remind ourselves today, to generalize this and talk about states themselves as operators, and we call those the density operator, written here as the outer product of the vector with itself, okay, or a projector onto that state. So in the basis, these are the matrix elements. They're bilinear, these coefficients. And importantly, it's extremely important, the diagonal elements of this operator, the density operator, are what we call the populations. This is a jargon that we use, really comes from thinking about, sort of an old-fashioned point of view of rate equations, as we'll see. But what these diagonal matrix elements are, they tell us what is the probability to find that particular outcome. So the diagonal matrix element tells us about the probability of finding a particular outcome. Okay. The off-diagonal elements we call the coherences. And they're called the coherences because, as we know, coherence means something about interference. And so what the off-diagonal matrix element tells us is something about how interference can occur, quantum interference can occur between those alternatives, and how that interference would affect a particular measurement outcome. Okay, and as an example of that, last time we looked at this, said, well, let's consider a spin 1/2 particle. We can think about different bases, the eigenvectors of spin along z, or the eigenvectors of spin along x, and we have some relationship here between those eigenvectors. So if we look at the specific example, as an example, let's suppose you prepare the system as spin up along the x-axis. The density operator is this operator written in that basis is this matrix, right? It's the outer product of the vector with the ket with the bra. Or in the z basis, and sorry, my mind was, I don't know what I was thinking last time when I was thinking about a change of basis matrix rather than the density operator, so why I screwed up last time. But anyway, obviously this is the density matrix written in the z basis. Okay. Now, one thing I just want to note here, I noted this last time, I just again, it doesn't make sense to talk about the off-diagonal matrix elements. Off-diagonal matrix elements depend on the basis with which it's a basis-dependent question. So in this basis, there are no coherences. Okay? Whereas in this basis, there are coherences. one shouldn't confuse, as well, the term coherences with purity, which we'll come to in a moment to remind ourselves about that. So, what do these, how do we interpret then again the notion of coherences? Well, if we looked at the specific example of this, let's say we prepared the state, so we were given that the state is prepared to spin up along x, and we want to know what is the probability for finding it spin down along x. Well, obviously that's 0, right? Because these are orthogonal states, and it's strictly 0. But just being kind of silly, pedantic here, is to emphasize an important point. So by the rules that we just established, if I want to calculate the probability of finding that outcome, I need to look at the diagonal matrix element of the density operator, right? That's what we just said is the rule. Now I can, because I feel like it, and I'm the boss, and that's nice once in a while, I'll change basis by shoving in a complete set of states along for spin up and down along Z, okay? And so I did that, and I get 4 terms here. And what we see in the first line of these 4 terms is what we would call classical logic, right? This is just conditional probability. The spin might have been up along Z, it might have been down along Z. Who knew? I don't know. And so if it's up, there's some probability that I'll measure up along x, given that really it was up along z. And then I weight that by the probability that it really was up along z. Or maybe it was down along z. And if it was down along z, there's some conditional probability that I'll find down along x, given that it really was down along z. But that would just be classical logic, and we know that ain't the whole story. That to get the actual probability of this outcome, I need to square the amplitudes, and that is reflected in these second terms in the sum. And those second terms in the sum, as you see, include the off-diagonal matrix elements of the density operator with respect to that basis. And each one of these guys is a half. In this case, everything here, this is a half, this is a half, this is a half, this is a half, as you count in the list. But this is minus a half. And this is minus a half. And so the total probability, as expected, is 0. Which is to say that there is a destructive interference, quantum interference, between the alternatives up along z and down along z, such that this total probability outcome is 0. Okay? All right. Very good. All right. So, now, as I said, I mentioned the term, and I'll remind everybody about the notion of pure states versus mixed states. If we have a vector in Hilbert space, we call that a pure state. And as we said, we can write that as a density operator, and I can write it the probability of any measurement outcome in terms of the Born rule. This is a form of the Born rule. We'll see many forms of the Born rule. Now, what other QLs we have? Well, we can imagine, well, before I say that, I wanted to emphasize one important point here, which is that the state tells us how to predict the probability of measuring outcome. That's what the Born rule is. And that's all the quantum state is. It's a vehicle for calculating the probability of measurement outcomes. Okay. Now, let's bring up something. Let's suppose I have a preparation procedure. So, when we prepared the spin up along X, we might have had a Stern-Gerlach device which was able to distinguish the spin up and spin down cases, and we blocked one of the ports, and I gave you the one that came out. That would be a particular preparation procedure. And then if we knew that that was it, we would assign the state spin up along X, and then given that, we can calculate the probability of any measurement outcome. Okay. So, but let's suppose we have a slightly different kind of measurement outcome. So let's say I have a Stern-Gerlach apparatus, which I'll just say is a black box. Let's say that it's prepared spin up or spin down along the Z direction, right? And so it has these two beams that come out, either spin up along Z or spin down along Z. Okay. Now suppose that, there's somebody there with a fair coin, and there's George Washington on the quarter. This is a sad state of affairs. Flip a coin, it can come up heads, or it can come up tails. Tail. Head. All right? All right. Well, give me a break. All right. So the point here is that the preparer is going to flip this beautiful coin and decide whether to spit out one of the atoms that comes out in this beam or another one. Okay. So if it's heads, she's going to spin up along Z, and if it's tails, she's going to spin down along Z. All right? So that's inside some big box, which has this, and out comes one of these spins. And now I want to do a measurement on this spin. And I want to predict the probability of finding whatever outcome I do, what's the probability of finding that outcome. All right? So, how would I do that? Well, I can ask, for example, what is the probability of, say, finding spin down along X? Well, how would I do that? In this case, if I know, I came in, I work with Alice over here, she's the preparer, and I know what she's doing, and we agreed you're going to do this. You're going to flip this wonderful coin that has heads and tails on it and decide whether to spit out. Then the way I would say, well, if Alice spit out the spin up along Z, then I know how to calculate. I can say that I use this form of the Born rule, and there's some probability, depending on the coin, that she did that, right? Or maybe she said, you know, it came out tails, and if it came out tails, then I would assign this. And that's how I would do it. That's how I would assign the probability to this. Now, I would like to be able to express this in the unified way to not have to think about sort of a conditional probability, but just say there is some quantum state. And I use my form of the Born rule that's up here to calculate that probability. So I want to assign a state of the system in this preparation procedure. So I can do that. I can just rewrite this by looking at this as follows. So I just unfolded those squares of the Born rules and used the linearity of the inner product to factor out. And what's inside here is rho, is the density operator. Because the rule says to calculate the probability of a measurement outcome, I look at the diagonal matrix element of some operator, and that's the operator with which I would take that diagonal matrix element, and that is the density operator. So this density operator is distinguished from this density operator. Let's write this out again. And just for simplicity, well, let me write this out now. This density operator for this particular case was equal to a half up along z plus a half down along z plus a half up along z, down along z, plus a half down along z, up along z, right? When I prepared spin up along x. However, so this is for this state, but for this state, let's suppose that it was a fair coin. So let's say that the probability of heads is equal to the probability of tails is equal to a half. Then this state is this, right? And what distinguishes those two states? What distinguishes the states is this state has coherences with respect to the z basis, which means that there can exhibit quantum interference between those alternatives. Whereas this state, if I write it as a matrix in the Z basis, has no off-diagonal elements, and thus there will be no interference between those alternatives. Of course, that's obvious that that must be true because of the procedure with which we prepared this. We prepared this by flipping a coin, classically, and deciding it would either up along Z or down along Z. In this case, we didn't prepare that state that way. We prepared it to spin up along X. Now, both of these states, if I were to measure whether it was spin up along Z or spin down along Z, what would I get in this case? Or say for the first case, if I were to measure this in the Z basis, and I wanted to know what's the probability of finding up along Z?
1/2.
It would be a half, right? Because it's just this. It's an equal superposition of up and down along Z. And similarly, this guy, if I measured and found down, it would happen with that. And that'd be true in this case too. So from the point of view of measuring along Z, they look the same. But if I measure along X, well, in this case, if I measure along X and I ask what's the probability of finding up along X, the answer is 1. And down along X, it was 0. What about in this case?
It's not even half that.
Let's just do it, just for the heck of it. Well, I mean, there's lots of ways to obviously see this. I mean, of course, this is 1/2 times the identity. But let me just be very quick here and just write this as a half times this plus a half times that. And each one of these guys is a half, so the whole probability is a half, as expected. And the probability thus of finding down along X is going to be equal to also a half. Right. If I had an unbiased coin, I mean a biased coin, one that had a different probability of finding up and down along Z, then I can calculate this equivalently. I can say, you know, the probability of finding, say, up along X would be equal to a half times the probability. I'm not going to do that because that's always going to be the same thing. So never mind about that. Okay. So the point here to emphasize here is that in this case we have a particular kind of what we call statistical mixture. A statistical mixture is a kind of classical probability of different alternatives in comparison to this state, which we wrote up here, which is a coherence superposition. And that's reflected in these coherences. wanted to emphasize. Okay. So, a pure state, one where I have complete information about the state. If I have the most possible information I can possibly have about the preparation procedure and everything else, then I would say it's pure. It's a pure state. Now, it doesn't mean the craziness about quantum mechanics is even if I have absolutely complete information about the state, it doesn't mean that the probability of seeing a certain measurement outcome is going to be deterministic. It can still be uncertain, even though I have absolutely maximum complete information. Okay? A mixed state is one where I have incomplete information. Now, the information can then be completed somehow, if that information, if it's incomplete in this sense of the word, then in principle it can be completed. And if I have that information, I have more information to be able to better predict measurement outcomes, right? For example, in what we just described, the missing information in that case was whether that coin was heads or tails. Now, there's one thing to note here. That means that the state is subjective. The preparer who spit out the spin, she knew whether it was heads or tails. And so from her perspective, it was a pure state. It doesn't mean that the measurement outcome was going to be deterministic, because if Bob decided to measure in the X basis, he will get a random bit. But she knows when it's going to be 0 if he measures in the Z basis, because she prepared in the Z basis, right? So it doesn't make sense to talk about the state of the system. It makes sense to talk about your state of the quantum system. What you assign based on what you know. Now, one of the examples, so the example I just gave you is a little bit of a contrived example with preparers, because it's not so contrived these days. People will think about communicating information stored in quantum bits, and they might do such a kind of preparation procedure. That's the kind of thing people think about in quantum communications. But there are sort of other examples which happen in physics. We can have that incomplete information. So if we have an open quantum system, meaning that we have a quantum system coupled to an environment, then the degrees of the freedom in the environment might be correlated with the degrees of freedom of the system, and have more information about the state of the system than I have. If I could look at the state of the environment, I would be able to complete the information, but I might not be able to do that. For example, let's think about the example we discussed, I think last lecture, where we thought about collisions. So when we thought about our Lorentz oscillators, we thought about how collisions between those atoms could cause elastic collisions which disrupt an oscillation. And if I didn't know when that collision would occur, if I averaged over many members of the ensemble, I would see this kind of decaying exponential of that, right? Let's think about this from the point of view of the quantum mechanics. Let's say I have my two-level atom, as we'll discuss more soon. And we know that the state of the system, in this case it was pure, in this basis of two levels is some superposition of the ground and the excited state. Okay? Now, if I have a collision between these two atoms, and that collision is an elastic collision, one that doesn't cause the population from the excited state to go to the ground state or vice versa, then the way we would model that is we would say that there's some energy associated with that, integrated over some time, gives me a phase shift. So I might get a relative phase of the ground state relative to the excited state. I'll just put that phase like that. Okay. Now if I knew what that phase was, it's a pure state, because I have complete information. But if this is in some kind of thermal gas, and it's getting a random phase at a random time, then the state I would assign to the system would not be this. What I would say is, well, let me write it over here. The state of the system, I have to somehow say, is a statistical mixture of possible states depending on what phase shift occurred, which I don't know, because I don't have complete information about the trajectories of all the particles in the gas, right? So what I would say is if there's a particular pure state, that particular pure state would look like, well, it has some population in the ground state and some population in the excited state. And it would have octagonal elements Let's kind of right? So that's that particular pure state. However, if I have some kinetic theory of the gases, and God knows you probably never have to think about that in this course, but you know, it's still physics. Then we move on to do some appropriate averaging. And we say that the state of the system is now a statistical mixture. I'll just write it like that. Of those states, weighted by the classical probability associated with that particular phase shift. And so my state of the system in that case, well, it wouldn't affect the populations if this was an elastic collision. But the inelastic, but the off-diagonal terms now are going to be averaged. Plus Hermitian conjugate. And so typically the effect of the collisions will be to wash out these terms. Because typically the probability distribution will be in such a way that for a long enough time, long enough collisions, this would go to 0. And the system would go from a pure state, which existed in a coherent superposition of regularly excited state, to a statistical mixture, which involves just statistically, it's either in the ground state or the excited state. I don't know which one, but I've lost the coherence. This is the quantum mechanical analog of what we discussed for the Lorentz oscillator, where I had these kind of interrupted wave trains with collisions and a phase shift, such that when I averaged over them, I lost my coherence, which represented by a decay of these oscillations. Quantum mechanically, we see that in the loss of coherence is a dephasing would mean a damping of the off-diagonal elements of the density matrix. In this case, we'll talk about that. This is one of the, collisions with background gas kills ion traps because it can cause dephasing, for example. All right. Very good. So let's summarize some things about the formal properties of the density operator. All right. Firstly, so we can write a density operator. One way to think about it, as we just described, we'll come back to this, is what's known as the ensemble decomposition. Which is to say, I have some states that are prepared with some probability, which means that the density operator in this case is a statistical mixture of those states. We saw an example of that with the coin flip, right? So there the ensemble was either up along Z and down along Z, and then I had the probability of having heads or tails, and I would take the sum of that, okay? What do we see about this kind of operator? Firstly, it's Hermitian. Right? Because these are positive real numbers, meaning really non-negative. Okay. So this is clearly our Hermitian operator. The other thing we know about this state, or this operator, which is the quantum state, is that it's positive. What does it mean for an operator to be positive? It means that it's that if I look at the matrix element with respect to any state, that this is non-negative. Now, how do we know that's true? Well, one way we know that's true is that the diagonal element is supposed to be a probability, right? therefore, and we see that in this particular case. And since it's Hermitian, I mean, it's got to be Hermitian if we're going to talk about it to be, it's a real number, greater than or equal to 0. Another way to say that is that this has its eigenvalues are greater than or equal to 0. So it's a Hermitian positive operator. That's basically it. That's what we demand for this to be a density operator. And a density operator is another word for the quantum state. You should forever and a day think about a quantum state is a density operator. Right. Now, as we always do when we think about quantum states, we normalize them. Actually, before I do that, let me say something different here, which is that if this guy is a Hermitian operator as positive, then I can diagonalize it. So here the E's for I's are the eigenvectors of the density operator, and these are the eigenvalues. Because I can always write any operator in the basis of its eigenvectors, and it's a diagonal matrix. Right? This operator in this basis is a diagonal, and D is the dimension of the Hilbert space of interest. Right? Notice the density operator is a statistical mixture of its own eigenvectors, weighted by its eigenvalues. So the eigenvalues of the density matrix tell me about that I can always think about the density operator as a statistical mixture of its eigenvectors. One thing that to emphasize here is that the ensemble decomposition is not unique. We'll study this more in detail. But for example, I could say flip a coin and send out spin up along X, or flip, if I get tails, spin down along. See, that's a possible preparation procedure. But these are clearly not the eigenvectors of any Hermitian operator. Why? They're not orthogonal, right? But it's a perfectly good preparation procedure. So that means that rho, let's say that this was a half. I mean, I can go half up along X, a statistical mixture of this kind. It's a perfectly good operator. Why not? I like it. It's an operator. It's positive. It's Hermitian. That's all I need. Who needs more? That's all you need. And if you have that, it's a density, but those are clearly not the eigenvectors. So the ensemble decomposition is not unique. We should ask, and we will, what is the constraint? How are different ensemble decompositions related to one another? They're not unitary transformations, because these are not bases. Right? It's a different idea. All right. Now, one thing to note about this is that the trace of the matrix, or the trace of the operator, is the sum of its eigenvalues. Right? And if I want this to be normalized, then I want this to be a good probability distribution. That's to say, I want to say, I can think about rho as a statistical mixture of its eigenvectors weighted by probabilities. Then the sum of those probabilities should be what? 1. So if it's normalized, 1. Now, importantly, the trace of the operator is basis independent. So I don't have to first find its eigenvalues and sum them. I can just find the trace of the matrix in any representation, or by any hook or by any crook I like, and it's always going to be the same. The trace is the same, but it can be always thought about as the sum of the eigenvalues, and as the eigenvalues represent the probabilities in a statistical mixture, then if I want to normalize it, I would say a normalized density matrix is 1, that's a trace of 1. As Sam astutely saw that I screwed up right away by noting that the trace wasn't 1. It's got to be. If I normalize it, it's going to be 0. That would be really bad. Because if it wasn't 1, I could always just divide by the trace, and then that's how I would normalize the matrix. I can't divide by 0. All right. Let's see. What other things do I want to say? Yeah. Okay. So pure versus mixed. Now, given a density operator, I should be able to determine whether or not that density operator is associated with a pure state or a mixed state. Okay? If it's a pure state, then in the basis of its eigenvectors, of course, ordered in some way, it's just this. Because it is the projector onto one of those eigenvectors. Because if I were to, for example, have the state psi as a ket and the density operator as the ket bra, then I can think what are its eigenvectors? Well, this is one of the eigenvectors. Psi is an eigenvector of rho, right? If psi, and with eigenvalue 1. And then all the other, any other vectors that are in the orthogonal complement to this are eigenvectors with eigenvalue 0. Okay. Notice in this case that the trace of rho squared, well, rho squared is equal to rho, and so this would equal 1 as well. We could see that in another way. If I look at a pure state and I square it, I get that, because I get the state back, right? And then if I take the trace of that, I get 1, yet again. So for a pure state, one litmus test of purity is to look at the trace of rho squared. The trace of rho squared will be 1 if it's a pure state. What if it's a mixed state? Well, if I look at, let's write rho in the basis of its eigenvectors, as we did. Then what is rho squared in that basis? All of those, right. So I just square all the, in the diagonal representation, I can just square the eigenvalues. So the trace of rho squared is the sum of the squares of the eigenvalues. Now what can I say about that? What is its maximum possible value and what is its minimum possible value? First of all, let's say this is normalized. So all of these guys are between 0 and 1. There's some positive number smaller than 1. So what can you tell me about this thing? It's certainly less than 1. It's only equal to 1 if I have a pure state. And what's the minimum possible value? Assuming a finite dimensional Hilbert space of dimension d.
So what about my
Let's see. Well, the minimum, which should be for the case where I have the state that is the most mixed it can possibly be. To be completely mixed is to say I have a statistical mixture which is a uniform distribution over its eigenvectors. If it has more of one eigenvector than another, it will be sort of more pure, right? So a state that is the most mixed, a maximally mixed state, all of these guys will be equal. And if they have the sum to 1 and they have d of them, they're 1 over d. So this is 1 over d times that for a maximally mixed state, right? Which is 1 over d times the identity operator in d by d space. All right? So the maximally mixed state is, as a matrix, is the identity matrix with 1 over d out front. So what's trace of rho squared? Well, rho squared, in this case, is 1 over d squared times the identity matrix. But you take the trace of the identity matrix, you get d. So the minimum possible value here is 1 over d. So the example that I gave you where I flipped the coin, if the coin was a fair coin, that would be the maximally mixed state. In which case, if I have the maximally mixed state, let's just say a quick aside over here. If I have a maximally mixed state, and I want to know what's the probability of finding a measuring outcome if I measure in a basis. So I measure in a basis. There's some basis and there's some, I want to know what's the probability of finding outcome alpha. According to the rule, that's that, right? I look at the diagonal matrix element of density, which is what? 1 over d. No matter what I measure, doesn't matter, I'm always just going to get a completely random outcome. A completely random outcome in d dimensions is 1 over d. So in some sense, this is a completely random state. It has no information at all. There's nothing to learn about the system if it's in the maximally mixed state. It's completely random. There's no quantum interference anywhere, anytime. Okay. So, as I said, the density operator equivalent to the quantum state, which is equivalent to a vehicle for determining the probability of measurement outcomes. Right? So we already said that right over here. If I want to know what's the probability of finding alpha, I do that. Now, another way to write this that you will see is useful is the following. I can write this as the trace of rho with that projector. Something, a little exercise if you've never done it, we'll do for homework next week. It's the famous rule. So, for a little aside, if I look at the trace, a trace turns an outer product to an inner product. I take the bra and the cat. You got to make the noise because then you remember it. It clicks on as a Lego brick. So if I want to take it, that's how I find the trace. It takes an outer product to the inner product in that way, always. Okay. So this is one form. We can think about this as the trace of rho with a projector. Onto that direction in Hilbert space. Okay. In fact, we know that the projectors onto the set of all base elements of the basis form a resolution of the identity. Right? And this is, I can think about as an example of, I'll give this a very heavy-handed name that will unpack as time goes on. This particular resolution of the identity is known as a positive operator valued measure, also known as the artist, formerly known as Prince, or POVM. We don't call them positive operator valued measures anymore, we call them POVMs, or just a symbol. This is an example of a measurement where the POVM elements, the elements of the POVM, which are these, are projectors. So this is an example of a projected measurement. We'll talk about more general measurements as time goes on. But this is the Born law. It's the moral equivalent of psi star psi. Gives you the probability density for finding an electron in a cloud. This is a fancier way of saying the same thing. Okay. So to find the probability of measurement outcome, to each measurement outcome, I assign an element of a POVM, and I take the trace of rho with the POVM element, and that gives me the probability. That's the rule. Now, why the hell do we call this a POVM? What's the point of that? Just, oh wait, we'll talk about that. Yes, sir.
Can you, I'm a little bit scared of that pi alpha. Does that mean that you have a product state?
No, it doesn't mean that. That, we should be careful, and it is a little bit, this, let me write this clearly, is an outer product. An outer product.
Well, I'm sorry.
Yeah.
I thought that thing on top of the capital pi was
It's an operator.
it's a hat. Okay.
Yeah.
Okay.
And outer product, as you may or may not remember, is an operator. This is a matrix, right? If I wanted to write it in a basis. What you were describing as a product state is a tensor product, right?
Yeah, no, the reason, I thought that pi alpha was somehow the product sum. I thought it was like a sum of alpha.
Yeah. No, I'm sorry. Yes, it's not, yeah, that's an I don't mean this as a product over anything. It's just the use of the capital pi for a completely different purpose. It's a projection operator is what we call it. It's the equivalent of a dyadic, if that helps or hurts or scared or more scared. All right. Expectation values. Okay. So let's say I have an observable, a Hermitian operator, A, which has eigenvalues alpha and eigenvectors K alpha. These are now the eigenvectors of the observable A, and alpha are its eigenvalues. Okay. If I want to find the expected value, well, according to the rules of probability, I weighted the possible values of A by the probability of finding. Right? That's how you find average values. But the probability that alpha will occur in a measurement is given by the Born rule, which I can write in the trace way like that. Clear? Now this, how would I simplify that? Well, the trace itself is linear. The trace of the sum of matrices is the sum of the traces weighted by, so I can bring the trace outside the sum. Write that like that. Everyone clear about that? And what is this guy? That's the operator A. So to find the expectation value of an observable, I take the trace of rho with the observable. Okay. That's not the same thing as this. This is about the probability of finding a particular outcome, but they're closely related, right? Because the expectation value, I weight those by the eigenvalues, and that's how this all came together. All right. Okay, next thing. Maybe I'll write that up here, a little more room. Find my eraser, what did I do with the front? There it is. time evolution. So we, of course, given the quantum state at some time, I want to know how to update the state at later times. Right? Now, if I just, no measurements or anything have happened, then the state should evolve according to the Hamiltonian. So let's talk about Hamiltonian evolution. Right? Of course, we have, if I have a pure state written as a vector in Hilbert space, then we have the Schrodinger equation. And if H, well then of course I can also write this in terms of the unitary map of the initial state. And ut is equal to u minus I h p if h is time independent. All right. So what about the density operator? Well, if I have a pure state, rho at time t is the outer product of silence itself, right? And so if I wanted to ask what is the differential equation that describes this, I have to take the time derivative of the ket and the time derivative of the bra. So that is equal to minus I h bar h psi plus the conjugate of that, which is psi h bar psi h dagger, but h is Hermitian. Which is equal to minus I h over h bar rho plus I over h bar rho h, which is minus I over h bar, the commutator of h, which rho. Right? Now, note, this is the Schrodinger picture. This is not the Heisenberg picture. In the Schrodinger picture, the state evolves as a function of time. The state evolving as a function of time means, in this case, the density operator evolving as a function of time. And it evolves as a function of time according to this equation. This equation is sometimes known as, it's the Schrodinger equation, but it's sometimes known as the von Neumann equation. Because it was really von Neumann who dealt with the density operator first and introduced it into quantum mechanics. So a lot of people of a certain generation call this the von Neumann equation. Question for you folks, in the Heisenberg picture, if I have an observable that I think of as evolving as a function of time, what is the differential equation for this?
It's the same but with the opposite.
Exactly, it's the opposite sign. And I like to write it like that. Now, if I were to ask something, for example, about how the expected value evolves as a function of time, I could do that in either the Heisenberg picture or the Schrödinger picture. Dealer's choice. So if I wanted to ask, what is the expected value of A as a function of time, I could say, well, that is equal to the trace of A with rho of t in the Schrödinger picture. Or I could say the observable evolves as a function of time, and the state is fixed. That, my friends, as you know, is called the Heisenberg picture. And they should be the same thing, and they must be. And that follows here. So if I wanted to ask, how does this guy evolve as a differential equation, as a function of time? Well, I could do this in either way. Let's do it in the Heisenberg picture. So that's the trace of the observable. Yes, sir.
On the one hand, we were saying that in the Schrödinger picture, the operators are time independent.
No, bad use of words. I never used the word operators are. I said observables are. This is what is confusing. We shouldn't think about operators versus vectors. Scrap that from your undergraduate mind. We're talking about states versus observables. And states are also operators. The state is the density operator, and the state in the Schrödinger picture evolves as a function of time, but the observable is time independent. In the Heisenberg picture, the state is fixed, but the observable changes. It's not operators versus vectors. It's states versus observables. That's what's confusing if you're not familiar with it. Now is the time to learn. All right, good. So with that said, I'm calculating, for the heck of it, this expectation value, and asking what's the differential equation for how it evolves as a function of time. If I do that in the Heisenberg picture, this is what I'm going to do. And according to this, in the Heisenberg picture, this was equal to minus I over h bar, the trace of the commutator of A with h with rho, because of this equation that we wrote over here, right? Now, do a little dance and make a little something and see how this works out. I'm going to expand this out. Okay? So I just expanded out the commutator. Now, let's do a little aside over here. We have an important rule of trace that we will remind ourselves of. If I have three matrices, A, B, C, then I can permute them cyclically, and the trace is the same. If I do a cyclic permutation of those matrices, the trace is the same. So, this trace is equal to the trace of rho. No, I'm going to leave that one alone. And write this guy as the trace of A rho h from the cyclic property, right? I can move this to the other side. But notice this is equal to minus I over h bar, the trace of A with the commutator of h with rho. Because this is h rho with a minus sign rho h, which is the commutator of h with rho. Which is to say that this is equal to the trace of A with the time derivative of rho in the Schrodinger picture. It didn't matter. It should be the same. I can use the Heisenberg picture or use the Schrodinger picture. It doesn't matter. Dealer's choice. I'll get the same matrix elements in this case. It's about expectation value. Okay. All right. Kind of finished on time. Any questions? Yes, sir.
Midway through the lecture, you said in density operator representation, you don't even have to choose orthogonal states. I mean, I guess you need to choose states that span space, but they don't have to be.
I can have a preparation procedure. I can have what's called an ensemble decomposition of a statistical mixture of vectors which don't have to be orthogonal. Now, I know this is a little bit puzzling because we haven't seen this before, and we'll get into this a little bit more deeply, but one shouldn't think about this as different bases. They're different members of an ensemble. And we'll have to study, we'll do that probably after a little while, how to relate, given one ensemble decomposition, what are all the other possible ensemble decompositions that correspond to the same density matrix. And this is one of the weird things about quantum mechanics. In some sense, the classical probabilities and the quantum superpositions get mixed up with one another. And from the point of view of the observer, you can't tell the difference. The statistics that you see in a certain measurement outcome could have come from, you know, the observer cooking up the little gremlins, cooking up the spins underneath the machine, spin up and down or at 45 degrees in all kinds of ways, and it would look the same to you. From the point of view of you do a measurement, you see some outcome, something, and do it over and over again, and I build up some statistics, you can reconstruct the density matrix. It's called quantum tomography. However, you wouldn't know the preparation procedure because it's not unique. It's a strange beast. We'll see more of it as time goes on. All right, have a good afternoon, everybody.
If I can add
Yeah.
to that, a very elegant solution to that problem of declassification of ensembles was given by Michael Nielsen using the concept of majorization. It's a paper from 2000, I think.
We'll have a homework problem on it. It's take a little time for us to get there. Yep. All right.